Drawing and evaluating resonance contributors. Have you got it? In this short video quiz, we're going to look at resonance contributors, how you draw them, and how you can judge which contributor among a set is the most representative or the most significant. As with all of these quizzes, the quiz consists of 3 questions, and it's meant to be taken after you've studied the material and think you understand it. During the presentation, you'll be asked to pause the video, to at least try to solve the problem yourself, and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, given the structure below, propose 2 additional related resonance contributors having the same number of double bonds. Which of these 3 resonance contributors will be the most significant, the most representative of the actual species? So pause the video now, get out a sheet of paper, write this down, see if you can do it, and then come back to the video and continue. I'll wait for you. Okay, how did you do? We start by looking at this system, and we're looking for 3 atoms that are adjacent to each other, 2 with a double bond, and 1 with a pair of electrons or a charge. And I think you can see here, in this top, we have a double bond to oxygen and a minus charge next to it. So if we redraw the full sigma structure of this compound, and we leave everything else the same except those 3 atoms, and switch where the double bond is and the charge is, we have another resonance contributor. Okay, and if you look again over here, there's also a double bond on the other side of the minus charge, so we can do it over there as well. Leave the carbonyl group this time exactly where it was, and put the double bond up there, and the minus charge goes to the nitrogen. So we have 3 resonance contributors. All of them have 2 double bonds and a minus charge. And the question now is, which one of these is the most significant? All right, well, the main difference among these is where's the minus charge. And the one on the left, we have the minus charge on nitrogen. The one in the middle, it's on carbon. And on the right, it's on oxygen. And we know that oxygen is more electronegative than nitrogen, and nitrogen is more electronegative than carbon. So oxygen is the most electronegative atom here. We've delivered the electrons to the most electronegative atom, and that is going to be our preferred, most significant structure. So, how'd that go? Number 2, given the structure on the left, propose at least 2 additional related resonance contributors. Which of the 3 contributors will be the most significant? Pause the video, try this on paper, and come back. I'm going to go have a cup of coffee in the meantime. See you soon. All right, you're back. Let's see what we've got here. In this case, we have 2 double bonds and an atom over here, this oxygen, which has 2 lone pairs, one of which can be in a p orbital and interact with the p orbitals of the rest of the system. So we have 5 atoms, and we have 2 double bonds, and we have 1 lone pair that can get involved here. And particularly if we look at this, I think you can see that that lone pair on the oxygen, the one we're really interested in, the one that we're thinking of in the p orbital, is in fact adjacent to a double bond. So here we go. We draw the structure again. Be sure you draw the full sigma structure. Just carefully copy it exactly as it is. We're only going to look at these 3 atoms that involve the double bond and the lone pair. And what we're going to do is we're going to share that lone pair with the carbon. That will put a plus charge on that oxygen because we're sharing an electron. And we're going to deliver the electrons to the nitrogen. So it becomes neutral. And that's actually pretty good. We've got still 2 double bonds, and we have a lone pair. Now, what else could we do? Well, if you look here, now involve this nitrogen with this double bond. What do you think of that? If we have a lone pair, we have a double bond. Let's try it. Here. I'm going to leave the left side exactly the same. This time I'm only going to look at the right 3 and swap the double bond and the lone pair. Now look, I've got a lone pair out here on carbon. Do you remember what that means? That means that's going to be a minus charge, and I have 4 bonds to nitrogen, so that's going to be a plus charge. Well, you could say that that's not a really good idea. So what do you think? How does that look? We have 2 positive charges and a negative charge. Maybe not so great, right? But on the other hand, it is a resonance contributor, and the problem does not state anything about how great a contributor we have to make. We could consider this done. But I want to point out that there's actually another way we could do this and probably come up with a better resonance contributor. And that is, and maybe you figured this out on your own, that if we have this system over here that has the nitrogen double bond to carbon, one of the things we can always do with a double bond is simply deliver the electrons, assign the electrons in this resonance contributor to one of the atoms instead of sharing. And in this case, the natural choice is to send the electrons to the nitrogen, which is already positively charged and will become neutral. So another resonance contributor we could have come up with would be this one, where that lone pair now is on nitrogen and there's a plus charge on the carbon. And this actually is the resonance contributor most organic chemists would probably write as a significant, but maybe not the most significant contributor. Because after all, now we only have 1 double bond. And so because we lost the double bond, this is not going to be the most significant. This is a less significant resonance contributor. Okay, we know this is a really not significant resonance contributor over here with the 2 pluses and 1 minus, too many charges. Too few bonds. And that leaves us our first 2 to consider. Now, what's the big difference between these 2? Where the plus charge is, right? The plus charge is on the nitrogen, or the plus charge is on the oxygen. Now, thinking about electronegativity, where would we like that charge to be? Well, it represents an atom that has lost some of its electron density, so preferably that electron density would come from the less electronegative atom, the atom that's holding on to its electrons less tightly. And so in this case, it's the one that we started with. We're actually not going to be able to beat that with drawing new resonance contributors. Our best resonance contributor has 2 double bonds and the plus charge on the less electronegative atom. All right, ready for number 3? Here we go. Here's a challenge. Given the structure on the left, determine all possible resonance contributors having 4 double bonds. Wait a minute. Doesn't this have 3 double bonds? Where's my 4th double bond? Well, I think I'm going to give you a clue here, and that is that when you do this problem, you should consider what this really means right over here. This is called a nitro group, as in nitroglycerin and trinitrotoluene. And that nitro group has a structure, and you'll want to think about what that structure is. Now, I'm not sure I recommend doing this entire problem. See what you can do. Give yourself a certain amount of time, like 5 minutes, and see how many of these resonance contributors you can bang out in that amount of time. I'm going to give you a clue right now. There are 11 resonance contributors in this set. So, good luck. Maybe time yourself for 5 minutes, see what you've got, and come back. Okay, we're back. Now, one word of caution here. We actually cannot do anything with these resonance contributors until we lay out the entire structure without any abbreviations like O2N. So really what we need to do is draw this again and consider what we actually have. Now, you probably know now that the way we're going to write this nitro group is like this. It's a system with 2 pairs of electrons on an oxygen doubly bonded to nitrogen, 3 pairs of electrons on an oxygen singly bonded to the nitrogen, and there's a plus charge on the nitrogen, minus charge on an oxygen. Well, right there, if we look at that, think about it, there's our little system with a double bond and a charge. So what we can do is immediately draw a similar structure, everything the same over here, all the bonds in the same place. But over on the nitrogen, we would have the double bond, other oxygen, and the minus charge on the other oxygen. Okay? Now, if you look carefully, you'll see that we have, in addition to this, in both of these cases, I'm going to run in parallel now. In both of these cases, we have our little system with 3 atoms, a double bond, and a charge. So what we can do is draw that, switching the double bond and the charge. That pair of electrons, we're going to donate a pair of electrons into the ring, and it's going to show up on this drawing, at least the skeletal drawing, just as a minus charge. And I'm going to go back and just write this as NO2, and I'm going to say, hey, Prof, this is the same here. Okay? And maybe they'll be kind to you. Over here, I'm going to put my minus charge there, and that's also my NO2. In fact, I could just not even do that and say ditto for this one and keep going here. So here we go. All right. And how about one more over here? Keep going around the ring. I like playing checkers or something like that. Hopscotch. And then keep going. We can end up back on the oxygen. How's that? So from this structure, I have 1, 2, 3, 4, 5 structures. And from my other structure over here, I could also draw 4 more structures. I would just draw the nitro a different way. So that makes 10. But there's one more that is kind of interesting. that we could easily skip here because I'm cutting corners. But if you look carefully, you see that in both of these structures, there's a double bond right next to the ring. And in this particular structure, there's a minus charge on the ring at that point. So this structure actually can contribute one more possible resonance contributor by taking that minus charge and delivering it to the nitrogen, sharing those electrons with the nitrogen, and putting the charge on the two oxygens. And that makes our 11th structure. Okay, so little challenge there, thinking about what a nitro group is, and then lots of structures, and just keeping going until you have exhausted the possibilities. Okay, what have we got? Remember, resonance structures generally involve two or more contiguous, meaning adjacent, sp2 centers, because electron delocalization of this nature exclusively involves overlap of p orbitals. So we can go from a set of 3 atoms with a pair of electrons on the left and a shared pair of electrons in this bond, and reassign those electrons so that the atoms on the left have the pair of electrons and the atom on the right has its own lone pair. And realize that it's not like this lone pair on the left is sort of somehow jumping over to the right. It's just a very subtle difference in representation. Okay? There's no actual motion here at all. It's just two different ways of saying the same thing wrong, basically. Remember that we can only put one pair of electrons in that p orbital. Remember, a formal charge or a pair of electrons on an atom adjacent to a double bond, often provides an opportunity to generate a new resonance contributor. The contributor with more electrons assigned to the more electronegative atom will be more significant. In this case, we have two choices. We've either put a lone pair on the oxygen or a lone pair on the nitrogen. And since oxygen is more electronegative, this structure is more significant. And even a double bond by itself can be used to generate additional resonance contributors. But be sure, if you do this, that you always assign the electrons to the more electronegative atom of that double bond. So in this case, for example, here we have a carbon-nitrogen double bond. We always want to put those electrons on the nitrogen, not the carbon. Carbon is less electronegative, so we're going to end up with the positive charge on that carbon in this case. Same over here. We have a carbon and an oxygen. We're going to assign the electrons from that double bond on the oxygen when we generate this new resonance contributor. And realize that whatever we do, because we broke a double bond, what we're making is going to be less significant. But it's still a perfectly good resonance contributor. All right, so there you have it. Some ideas for how to generate and think about resonance contributors. I hope now you've got it.